I'm going to teach this session sitting down here rather than looming above you up there, because otherwise I will lose my voice and my sanity. I don't bite. You're welcome to defragment and join me on this side of the room. I honestly don't care where you sit, just giving you the option. So yeah, let's begin. My name is Philip Paeps. I'm going to teach you a 3-day workshop on DNS and DNSSEC in the next 3 hours. It's a lot of material, and I don't think 3 hours really does it justice. But to be honest, I don't think 3 days really does it justice either. Before I get into the material, I'd like to throw up this slide and dwell on it for a bit. I'm just presenting this material. This slide deck has a very long history. Several of us have been teaching DNS and DNSSEC around the world in several internet communities for probably 20, well, not quite 20 years, 15 years at this stage. And we had a lot of slide decks drifting around of varying quality because, you know, usually we make these things 20 minutes before we start teaching. Last year, I think Awal did the Herculean task of taking several of our slide decks and putting them together into a very nice slide deck. So that's the one I will be using today. Credit where credit is due. It is, you know, it's my name on the title slide because I'm sitting here, hopefully entertaining you. But the slides are the work of several people, not least Awal, who polished them up and put them together to look nice as we're using today. So as I said, 3 hours is not enough. You will get something out of this. You will understand how the DNS works. You will understand how DNSSEC works, at least to some extent. But to really get and understand and be one with the protocol and its implications, you need to go home, sign your zones, and run a resolver, and just use DNS and use DNSSEC because that is the only way to learn. You need to go and break things and fix them to learn. So with all that said, let's go into day 1 of this presentation, which will take about 45 minutes if I have not lost my touch. Moving right along. So fundamentally, the DNS is a system that allows you to look up hosts by name and to look up the host names that belong to an address. So given a host name on the internet, say nsrc.org, as is the example on this slide, the DNS will tell you what its addresses are. It will tell you nsrc.org has this IP address. Fundamentally, on the internet, we address things by IP addresses. We don't address things by name. The DNS fills in that gap. It translates names to addresses. The DNS also does the opposite operation. Given an address, the DNS can tell you what name goes with that address. Or, as we'll see later, it'll tell you what name is associated with that address in the DNS, which is not necessarily a true fact. You can put anything you like into the DNS. The DNS is a source of truth only if you're willing to accept the truth. So there's a lot of history to the DNS. Before we had DNS, computers were very expensive and very large and very noisy. But more fundamentally, they didn't talk to each other so much. It was a much nicer world. The internet was very small and there were fewer than 1,000 hosts, or fewer than 100 hosts even. The first DNS was just a collection of bits of paper stuck to operators' terminals. So when these computers started talking to each other and people thought it was a good idea to string bits of wire between their computers and have them chat at each other, they put a little post-it note on their terminal saying, oh, computer X belongs to operator Y, and here's his phone number, and here's his IP address. And that's how it all worked. And this scales up to about 100 hosts, but clearly it doesn't scale much beyond that, because every time you change something, it's M times Y. You need to go and replace every single post-it. Mistakes will be made. So at some point, in the deep darkness of time, someone had a bright idea. Instead of having all these post-it notes stuck to all these people's terminals, let's go around, collect all the post-it notes and stick them into a text file and share that text file with everyone over FTP. And that worked. That worked pretty well for a while, everyone downloading the same file. It works really well as long as everyone agrees to download the file regularly, and as long as everyone agrees to actually keep that file up to date. If anyone was in my Let's Encrypt tutorial 2 days ago, you'll remember that I said that anything you need to do manually is something that you're going to forget. It's error prone, and it's just not going to be sustainable. So in the 80s, a distributed standardized protocol was developed to solve these problems. Instead of downloading a text file individually from the internet on every single host, there would be a distributed database that holds the authoritative answers for everyone, and it could be queried. For reasons of efficiency, it was decided that it should be running over UDP, primarily for latency, because you don't want to wait 2 RTTs to get your answer. Just ask, fire, and forget. UDP will give you the answer. Theoretically, the DNS just only indexes internet resources. So in theory, what's in the DNS is the IP addresses of the hosts, where to send email, what the web server is, and any other operational internet information is what should or ought to live in the DNS. But there's no real limit to what you can put in the DNS. It's a database. You can put anything that you can stick in a database, you can stick into the DNS. So over time, people have started sticking really silly things into the DNS, like geographical information. Where does this server live in the physical world on a cartographic point reference? More amusingly, people started putting public keys in the DNS to authenticate mail servers and all sorts of other things. People put really silly things into the DNS, and it works because the DNS doesn't care what you put in it. It's a protocol for answering simple questions and giving simple answers. So the data in the DNS are structured in a simple format, and it's indexed by domain name. So if you remember a database, any database usually has an index. The index is the thing you can look up, the thing you can query. In the DNS, that's a domain name. And in this context, a domain name is defined as a series or a sequence of labels. So in many other contexts, domain name is a top-level domain like something.com or apricot.net is a domain name. But as far as the DNS is concerned, www.something.com is also a domain name, or router a.rackb.datacenterc.something.net is a domain name in the context of the DNS. We think of it as a host name, but it's a domain name in the DNS. And these labels are separated by dots. So you walk down the DNS tree and you follow the dots to look up more and more specific things. Also, the DNS is only aware of case-insensitive ASCII labels. We'll see a little bit later if we get to it. I should maybe set a timer so I don't run myself out of time. We'll see later how you can represent other interesting scripts in the DNS, but by itself, DNS is purely ASCII. It knows about A to Z, 0 to 9, and a couple of funny characters, but not much else. When you put the DNS in a picture, you get a funny little tree, and the tree is upside down because computer engineers don't know how trees work. So the root of the tree is at the top and is known as dot, and you work your way down the tree to get more and more specific labels in the DNS. So in the dot zone are the com zone, the org zone, and the BD zone, and several others. And underneath com, you'll find google.com. Underneath org, you'll find any number of things. So it's structured like a tree. And if you keep the tree in mind, the fundamental algorithm of the DNS is walking the tree. So I'll talk about that a lot today. You walk the tree down from the root to the leaves to find the answers you're looking for. And every time you walk along a branch of the tree, we say that authority is delegated. So when you're at any level of the tree, you have authority. If you want to create something further down the tree, you delegate this authority. So I'm going through a bunch of terminology here. This will all make a lot more sense when we get further down. But the important thing about this slide is that nobody is in charge of the entire DNS. The DNS works because people delegate authority downwards. The people who run the dot zone have nothing to do with the data in the org zone. The people in the org zone have nothing to do with the data in the sanog.org zone. Authority is delegated, and everyone is responsible for their own data at their own level of the tree. So you delegate your authority downwards, and you follow the branches of the tree until you get the data you need. This is very similar to a Unix file system. If you're using Unix, the root of the file system / something, you can put that on the same sort of tree. You walk down to find the file you need. The DNS root is called dot. It's the empty label. There's nothing in front of it. It's just dots. It's the ends. Currently, there are 13 root servers in the DNS, A through M. There's 13 named servers, but there's about 1,000 instances because each of them is anycast. Underneath the dot, there's what we call the top level domains. There's more of them than we can count today. Under there, there's TLDs, CCTLDs, all kinds of things. They're all the same thing. They're different names for the first level of the DNS tree. But fundamentally, each of these little labels is independent of each other label. So dots controls only the top level. The CCTLDs only can control their own data. The GTLDs only their data. We'll talk about internationalized domain names a little bit later because I have a lot of material to cover and not a lot of time. So I'm going to talk about domains and zones almost interchangeably. And I want to get a little bit of terminology out of the way still. I promise I'm almost done with terminology. In the context of the DNS, domains are namespaces. So everything below .net is a net domain. Do the colors work on the slides? Yes, they do. So in the yellow bag on the left side of the tree, we call the com domain. It's everything that is underneath com. In the little blue bag is the net domain. Everything under net lives in there. And the green bag is the apnic.net domain. So you build little boxes and you put things in there, and we call them domains. And parent-child relationship should be clear to everyone by now. The org zone is the parent of bdnog.org. The bdnog zone is the child of the org zone. So this is all terminology, and everyone who does DNS uses all these terms all the time without thinking about it. But if you've never seen the DNS, you're stuck in a dictionary of words without knowing what anything is. So I hope these slides clarify things a little bit. If you still get confused, I don't bite to ask questions. Another piece of vocabulary is delegation. I mentioned it earlier. Delegation is the act of assigning responsibility to someone else. So I run the trouble.is domain. I am putting you in charge of apricot.trouble.is. I am delegating authority of this domain to you. You're now in charge. I don't know what you stick under apricot.trouble.is, and I don't have to care. And the link is in one direction. So the child doesn't know its parent, but the parent knows its child. That's a bit strange from a botanical point of view, but that's just how it works. Again, domains versus zones. I'm not going to dwell on this slide because we need to cover a lot more material. All of these slides have been uploaded to the paper system. Go and download them and study them at length. If you get confused at any points, just go back to the first dozen or so slides to refresh your memory. When we talk about walking the DNS, we talk about domains. We follow the labels of the tree down. So to resolve anything in the DNS, we just walk our way down the tree until we get the answer we're looking for. So delegation we discussed are the points where you move from one authority into another authority. Sometimes in older documentation, you'll see this referred to as a zone cut. I don't really see that word anymore these days, but documentation uses it. So you just keep walking that tree and you get there. There's a couple of restrictions. So DNS is an old protocol. There's a couple of restrictions on the kind of data you can put in it, but it's overall pretty flexible. A label can only be 63 octets long. So trouble.is, the word trouble, can only be 64 bytes long. IS can also only be 63 bytes long, rather. And the total length of a domain name can only be 255 octets long. So you can't have an endless string of letters and numbers or endless strings of letters and numbers pasted together by dots. It cannot be endless. The total length can only ever be 255 bytes. That's a pretty long string of text, but it's a limit that starts making sense when you start using internationalized domain names, because representing scripts other than English in text blows it up in size a bit. So English characters, 1 ASCII character equals 1 byte. But if you start writing Chinese, it's 2 bytes or 4 bytes per character. And then you need to go and encode this into Punycode, which blows it up in size even further. So the 255 sounds like a lot if you're thinking only of English text, but it's not really that much if you're considering other alphabets as well. Time to live we'll talk about later is a 32-bit number. Talk about that a lot later. The whole message of the DNS needs to fit in a single DNS packet. So for plain DNS without any DNSSEC, that's 512 bytes. That's the maximum size you can fit into a UDP packet without changing buffer sizes, without doing anything special. Any larger packets in the DNS by default falls back to TCP instead of UDP, so your latency goes up. More recently, there's a standard that allows you to tell your DNS server that, hey, I'm a computer built after 1980. I support buffers larger than 512 bytes. Please send me up to 4 kilobytes of data. That's called eDNS 0. We'll see a lot more of that in the second session when we talk about DNSSEC. But in its simplest manifestation, DNS fits in 512 byte UDP packets. And for the vast majority of simple queries, that's what the traffic is going to look like. Once you start adding DNSSEC or doing more interesting things with the DNS, the packets will start getting larger. And depending on whether your network is configured correctly, you'll start falling back over TCP and experiencing latency, or you'll start seeing things break because you have UDP problems. We'll talk a lot more about that later. This is just some preamble. The wire format of the DNS, I'm not going to talk about in any amount of detail during this presentation because we simply do not have time. I can try to speak really quickly to fit 3 days into 3 hours, but that's no fun for anyone. If you are interested in the wire format, go and download this presentation and read up on it. Or better yet, just run Wireshark or TCP dump on your own DNS queries and see what's happening on the wire. Or Warren is doing a packet capture tutorial on Thursday, I think, which is tomorrow, where you can see a lot of DNS packets in action in the flesh. You don't do DNS. Warren is going to add DNS to his packet capture lab before his tutorial tomorrow. Okay, Warren has a question. You want to go to the microphone so I don't have to repeat it?
So this is where bit squatting could come in as well.
Bit squatting. Yes. Yes. All right. I already don't have enough time. Warren is now shortening my time. Cool. So not going to talk about the wire format much. Look at your traffic in Wireshark and just take a look at what it looks like and go and see Warren's packet capture tutorial for a lot more on this. There we go. Recent DNS has internationalized domain names. I hinted at this. Again, I'm not going to read out all these slides at you because that's boring and you have better things to do with your time. I've hinted at IDNs. The only thing that matters for the purpose of today's tutorial is that it is possible to represent non-English scripts in the DNS. You can have Chinese domain names. I have one. You can have Bengali domain names. I think Awal has a whole bunch of them. You can put other scripts in the DNS if that's your thing. The only thing you need to keep in mind is the labels get longer, but the protocol is unchanged. Right, so with the vocabulary lesson out of the way and all the tedious bits, let's get into the much more interesting part of this presentation, which is the moving parts, the bits that operators actually run. Unsurprisingly, there are servers and clients because it's an internet phenomenon and servers and clients are what we deal with. There's a couple of different kinds of servers. And again, there's some vocabulary because it's an old protocol and people keep changing the names of things. We think of authoritative servers, sometimes called primary and secondary servers, and they, as the name suggests, keep the authoritative data of the DNS. They know what's where. They have the actual real answer. Someone goes and manually configures these things and says, this host lives at this address has that host associated with it. They're the authority, they're the source of truth. We have resolvers or recursive resolvers or caching resolvers. These sit in everyone's network and go and talk to the authoritative servers to ask for answers. So usually you as a client never really go and talk to the authority itself. You go and talk to your recursive server because it's much closer. It'll cache your data for you, and it's going to ask the authoritative servers your questions for you, and then it's going to remember the answers. So the recursive resolver is a lot closer to the client, and usually you have one in every network. I recommend running one in every laptop because the closer to you your resolver is, the closer to you can cache your information. And also, as we'll see in DNSSEC later, the closer to you can validate that nobody in the path is lying to you. There's also hybrid servers, which are both authoritative and recursive. So bind, the reference implementation of the DNS, is both. It can be a recursor and it can be authoritative. And it's just a configuration detail. More recent implementation of the DNS pick one or the other adventure. So NSD is authoritative only, Unbound is recursive only. Talk a little bit more about that later in this session. Finally, in the client side is your stub resolver. That's the thing in your computer that knows how to talk to a DNS server. So libc or the Win32 or whatever the API is called, as part of your operating system, knows how to send a DNS query to a DNS server. It will go and ask a recursive resolver, hey, what's this host? Or hey, what's this address? So three components: client side, there's one client that's just a stubby thing, sits on your laptop and sends queries and does nothing else. Recursive resolver sits in the network or on your computer somewhere as a process. It knows how to ask questions and process answers and send them back to you. And authoritative servers have the source of truth. They know what's where, and those are configured by humans. So humans go in and plug in the information they need to be authoritative for. Let's talk a little bit more about the stub resolver. The stub resolver is part of your operating system, but increasingly, this is starting to move into the web browser. So it's a little. It gets a little bit fuzzier over time, but fundamentally, this is the thing you as a human user configure your DNS server on. So it's often configured by DHCP for you, but if you have a static configuration on your laptop or on a router somewhere or a server, this is the address of the DNS server you configure, the server you talk to ask your questions. On a Unix system, etcresolve.conf is where you configure it. Usually people use DHCP these days. On Windows, it's hidden somewhere in the registry. Currently, in this day and age, most stub resolvers will cache information for a short amount of time to avoid asking the resolver questions over and over again. But historically, stub resolvers were pretty stupid. You give them a question, they relay the question to the recursor and don't think about it twice. So this think of this as just the C library, the thing inside your laptop that asks questions. Again, not going to dwell too much on this because we don't have time. Resolver, I'll talk a little bit more in depth about. Again, it's a recursive resolver. It's also called a cache. And for the next 20 minutes to half an hour, I'm going to use the word cache a lot because it's very fundamental to the DNS. The DNS caches everything at every layer all the time, and each cache is independent and times out by itself. The recursive resolver is a cache that sits in your network, and it answers questions, or it asks and answers questions for any number of hosts in that network. So they go through, they walk the tree for you. Remember my tree picture earlier? They go and walk down that tree and ask those questions. Hey, dear ComZone, where is google.com? Dear google.com, where is www.google.com? The recursive resolver is going to recursively walk down that tree for you, tediously and slowly, or quickly, and keep the answers for you so that next time you ask that question, it's just going to answer to you straight away. I remember that google.com is here. I remember nsrc.org lives here. Here's your answer. Now go away. So the process is iterative or recursive resolution, because what it's doing is it's just walking that tree. And fundamentally or critically, the resolvers will cache their results until the time to live expires. And again, I threatened you with a lot of caching words. The resolvers will remember your query results for a certain length of time. This length of time we call the time to live, and it determines how long data is or data are valid for. So you're not going to ask the DNS the same questions over and over again, because if you ask the same question over and over again, expecting a different answer, that's madness. So the DNS will optimize by remembering answers for you for a certain length of time. The address of apricot.net does not change every millisecond or between every query. The server will have the same address for months or years or longer than that. The DNS knows this or is aware of this phenomenon, so results are remembered for a configurable period of time, and the length of time is at the discretion of the operator. So as you put your data in the DNS, this host has this address. You also specify how long you can remember this address. So, you can, dear client, you can be certain that this name server or that this web server will not change address for the next hour or for the next day. Please remember this answer for the next day. And recursive or caching resolvers will do exactly that. They will remember this for you. So you might have 100 clients in your network talking to the same resolver. The first one will go and do the dance of looking up the authoritative answer. The second one will get it straight away from the cache. I'm not going to ask Apricot again. I'm just going to give you the answer I got last time, and you will be happy with it. And then your stub resolver will go and cache it as well, possibly for the same amount of time. And it's caches all the way down. So each of these timeouts independently, but the time the data are valid for is under the control of the operator. If we were doing a workshop, I would be doing a query for you right now, but I don't think we have time for the hands-on bits. The time to live, when you do a query on your laptop, you'll see it as the time to live field. And if you run your query over and over again, you'll see that number drop. So it starts out as a day in this example. It'll go down. If you ask the same question a second later, it'll drop down to a little bit less than a day, a little bit less than a day, a little bit less than a day. We'll do, in the second session, we'll do a lot of queries, and this will be more obvious. The first part of this tutorial is mostly me talking. The second part is going to be me typing. I want to talk a little bit more about the root servers, because that's where this whole story begins. The whole DNS adventure starts at the root. In order to walk the tree, you need to be able to actually find the tree. You need to have some kind of a server to ask the first question. You cannot ask where is the com zone or where is the org zone without having someone to ask about the root. So there's 13 well-known servers on the internet called root servers, and they're usually compiled in or configured as part of your DNS server package. They're well-known addresses. And the nice thing about the DNS is that the root servers also serve the root zone. So if you can reach any one of these 13 root servers, you can bootstrap the iterative or recursive algorithm and walk the tree down. So as long as you have one IP address of one root server that you can reach, and you can ask that server, hey, please give me the contents of the root zone, you can bootstrap the entire iterative resolving algorithm from there on. So if you have one IP address, you can carry on. So there's 13x redundancy there. Moreover, these 13 named servers are all Anycast nodes. So there's about 1,000 or so root servers in total on the internet. Again, a note on caching, many recursive resolvers choose to cache dot or the root zone locally because it doesn't change very often. It changes every couple of years or so when an organization renumbers. It's pretty disruptive. I can't remember the last time the root zone or the name server addresses changed. So that list of name servers is compiled in. The root zone itself, of course, does change. And with DNSSEC, it gets re-signed. And you can cache that zone locally as well if you like. But all you need to bootstrap the DNS algorithm is you just need to be able to resolve dot, or you need to be able to talk to one root server, and you can get it, and you can work your way down from there. Authoritative servers, again, I'm just going through this material really quickly. I'm not going to read out the slides because that's boring. Go read through these slides if I'm going too quickly. A root server is something that's configured by a human. So people like me go and sit down and we write text files saying, our web server lives at this address, our mail server lives at this address, our whatever lives here, and the other way around. This address is my web server, this address is my mail server, this address is my DNS server. And there's a bunch of different data types. We'll go through some of them later. But this is the authoritative server is configured by a human. So that's, this is the answer to the question at the end of the day. A human configures it. Different DNS servers have different formats. It's usually a zone file, a set of text records that goes down. Now we get to the fun bit. This is the DNS working mechanism. I'm going to leave this slide up for a couple of minutes because it's really fun, and Awel did a lot of work putting several ugly versions of this diagram together into a very pretty one. This is, if you take nothing else away from this presentation from the next several hours, this is what you need to understand about the DNS. So we work roughly from left to right in this picture. Your application on your laptop is going to ask, hey, I want to go to some web server. I'm a web browser, I'm Chrome, I'm Safari. I would like to go to www.example.com. I have a question, I want the IP address of this host. So what the client is going to do is it's going to send a little query. That's the red arrow number 2. It's going to send a query to the its configured recursive resolver asking, hey, I would like to know the IPv6 address of this. And the recursive resolver, ideally, if it's in the cache, the recursive resolver is going to say, yes, here it is, we're done. But let's follow the red arrows for the time being. If the recursive resolver does not have the answer in the cache, so if nobody else has asked this question before, the recursive resolver is now going to ask the question to the authoritative servers. But it needs to find the authoritative servers first. So the recursive resolver is going to ask, the root server, where do I find the com zone? Because if the cache is completely cold, the recursive resolver knows nothing. The only thing the recursive resolver knows is the address of the root servers. The cache is completely cold. There's no data in the cache. The recursive resolver needs to go to the root server, following the arrow number 3 here, the red arrow number 3. It asks the root server, hey, do you know www.example.com? Well, no, obviously you don't, you're not authoritative. Do I know COM? Yes, the root server knows COM. It's the root zone. COM is, its hopes and dreams, its joy in life is to tell you the address of the COM authoritative servers. So the root server goes back to the recursive server and says, you can find answers about domains ending in COM over here. Your recursive resolver will say, great, thank you, and walk on arrow number 5 to the COM server and ask, hey, do you know example.com? Well, no, because you're not authoritative. Do I know example.com? Yes, I do. Example is one of the things that lives inside the COM zone. So it tells you a recursive resolver, here is example.com. And the recursive resolver says thank you. Well, actually, it doesn't say thank you because it's UDP. There's no thank you. The recursive resolver takes this information and goes on and does exactly the same process again, right? I hope everyone is starting to see a pattern here. It goes and walks down the tree. It now knows where example.com is. So it goes and asks example.com, hey, do you know www.example.com? And finally, www.example.com says, yes, I know. Here you go. The recursive resolver is now happy. It knows everything, and it gives that answer to the clients. And we're done at this stage. Now, at any point of these red and green, this pair of red and green arrows, if an answer is in the cache, the query does not happen, right? Because you are allowed to remember the answers you receive for a certain amount of time. So every time you get an answer from these servers, they will also tell you how long you're allowed to remember it for. So during, remember our arrow number 3 and 4 here on the top right of the diagram, our little recursive cache is going to ask the root server, hey, what is the what are the name servers of the COM zone? The root server is going to say, here they are, and also please don't bother me with this again for the next day, because the people who run the COM zone are not in the habit of renumbering their network every day. So here's the answer, and leave me alone about this for the next day. Same thing, the next level down, the COM zone will say, when you ask for the example.com name servers, it'll say, here they are, these are their addresses, and don't bother me about this for the next day or whatever amount of time. And the recursive resolver sitting here in the middle is just, its joy in life is to remember these things for you. So it takes notes of these answers, and it goes and remembers them for a given amount of time. So if at any point you, the client, come up to the recursive resolver and ask it a question that it already knows, it's not going to waste its time getting answers to questions it doesn't need to ask. It's just going to say, here you go. And it's going to tell you the answer, and you can also go and remember it. So the recursive resolver also returns the time to live to you. So you, the client, will see www.example.com, and you, the client, can remember it for an hour or a day or whatever the authority has configured. And it's caching all the way down. And it's important to remember that all of these cache timers tick independently. There's no one big timer in the sky. Each record has its own time to live, and the time to live expires independently. So the recursive resolver, every time a question gets asked or every time a question needs to be asked, will look at, do I know the answer before asking the question, and keeps track of these time to live. So to give another example, if next time round someone comes around and asks not for www.example.com, but for something else or a second example.com, only this bottom right half of the adventure will take place, because the recursive cache is going to say, well, hey, I already know where the root servers are, and they told me not to ask again for the next day. I'm not going to ask. I know where to go straight away. I don't need to ask, well, I do need to ask the com zone where another example.com is, because I know where example.com is, but I don't know where another example is. So it's going to ask this guy, and then it's going to remember again. It's not going to bother asking this. If you have www.example.com, if you're going to ask for mail.example.com, the recursor is going to say, well, I don't have that answer. I don't need to ask dots because they told me to go away for a day. I'm not going to ask com because they told me to go away for 3 days. Example.com is the only guy I need to go and talk to, and he'll tell me mail.example.com is right here. And this is recursive and down the tree. So if you're 4 levels deep or 5 levels deep or 100 levels deep, the caches are independent. Your resolver is not going to ask questions it knows the answers to because they're cached. As an operator, the practical impact of this is that when you add your records to the DNS, you need to think about what sort of time to live makes sense. There's a bunch of sensible defaults. Usually people say things like an hour or a day, but the correct number to put in your authoritative DNS is the number that is correct for your network. The time to live you specify in your authoritative server is roughly the interval at which you mess with your network. Right. So if you renumber your network every hour, your time to live is an hour. If you renumber your network every week, the correct answer is a day. Why do I say a day? Because if you have to plan maintenance a week in advance, you're not going to have fun. So you need to wait up to that time to live before you can actually renumber your network without breaking the DNS. So if you have things that, if all your records have a time to live, if all your records have a time to live of 1 hour, you have 1 hour notice to do maintenance on your network. If all your records have a time to live of a day, you have 1 day notice to do maintenance on your network, because while that time to live is active, while someone remembers your answer, you cannot change it because someone is going to hit a warm cache and get wrong data. So the time to live is you, the operator, needs to set the correct value for your network. We are almost an hour, or no, we're about 45 minutes in. I will pause a moment for questions and to catch my breath. This was the first session of day 1, I think. I hope someone has questions. Have I put everyone to sleep? Did I kill anyone? Okay, so far so good. Feel free to heckle me as well if you like. The next section of this presentation is about the DNS packet, and I'm going to just skip it outright because if I talk through it without showing it in the terminal window, all of you will be comatose and none of us will be having fun. If you are interested in this material at all, please, again, do go and download all 260 slides of this presentation from the program and run some queries on your own laptop and just look at the packets on your network, because that is the only way to understand how this stuff works. For a lot more on packet captures, there's a tutorial tomorrow. The packets, while I skip through these slides, there's a couple of things I do want to say though. The DNS packets are fiendishly simple. They are really easy to understand, and the same packets is used all through these arrows. So the DNS query that the recursive resolver sends to the root, to the example.com servers, or the query that the client sends to the recursive resolver, these packets are all in the same format. It's just a couple of bits that are flipped. It's really easy and simple to understand. It's a protocol from the 1980s. It doesn't have much complexity. Don't be afraid to go look at the packets because you will understand the protocol a lot better when you do. So I'll just skip through these slides and not say anything and go straight into resource records. Resource records are the data items we plug into the DNS. So the resource records are what operators stick in their authoritative zones and what recursive resolvers query and return to clients. So that the resource record is the fundamental unit of data formally in the DNS. It groups a domain name, a type, and a class together with a time to live and the data. So it's a tuple of a name, a type, time to live, and then the value. The label or the name is what you are what you're indexing. As we saw at the very beginning, it's a sequence of things separated by dots with a dot at the end. A time to live. Every single record in the DNS independently has a time to live. The caching time or the length of time you're allowed to remember an individual datum that lives in the DNS travels with that individual record. So each record says, you can remember me for this long. Then there's a class. It's 2023. The only class that still exists is in. If you see any other class on the internet, you are being lied to. In is the only type that exists. This is a historical phenomenon. Ignore it. And we don't even type it in zone files anymore. Forget about it. The type of the record specifies what kind of data we have. So an A records is an address, not a lot of imagination going on there, A for address. And with the address goes some data. In the case of an address, it's a 32-bit IPv4 address. So each record looks like this. It's always in the same format. It's got a name, it's got a time to live, it's got a class you ignore, it's got a type, and it's got some data. The way the data looks differs a little bit depending on the type of records that you've got. So we'll go through a couple of them later, but not not in any tedious, exhaustive detail. Before I go on to that, though, I would say there's another term called the RR set, or a set of resource records, and that's a set of records which share the same name and type. So you can structure your DNS in a way that you can have multiple answers for the same question. So a given host can have multiple IP addresses. That's a DNS round robin. A given DNS server can have multiple names. Different types can exist at the same time under the same name, and they will all be returned. So when you ask the DNS for www.example.com, you will get all of these records. If you say, I want example.com A records, you will get both of these A records. You won't just get one of them, you'll get both of them. The order you get them in is unspecified. All that is specified is you'll get both of them. You will get all data every time. And the time to live is on the RR set, not on the individual label. So if you have two A records, both of them will share a time to live. They'll share a name, they'll share a time to live, they'll share a type, but they might have a different address. You'd use this if you have a server with multiple addresses or multiple servers answering to the same name. But it's worth remembering that if you ask for A records, you're going to get all of the A records. If you ask for quad A records, you're going to get all of the quad A records. If you ask for all the records and you don't specify a type, you're going to get all of these. So you can get, when you're looking at packet captures, do not expect, hey, I was only expecting one answer. No, the DNS is going to tell you everything, and you sort it out. It's a very simple protocol. Here is all the information you need to make your own decisions. The DNS considers the client to be an adult, for better or for worse. So a little bit more on types. I'm not going to go through these in tedious detail. Go read the slides. A couple you will encounter in daily life, though, are the address records. An A record is an address. A quad A record is an IPv6 address. Why is it called quad A? Because an IPv6 address is 4 times longer than an IPv4 address. So the imaginative people who come up with these terms, they just went, okay, an address is A, an IPv6 address is 4 times longer, just call it 4A. A CNAME is an alias. For the purpose of today's tutorial, that is all I'm going to say about it. CNAMEs are also evil and twisted, and they exist to make your life a living hell. but they are very useful and wonderful, just like all the other things that are evil and twisted and make your life a living hell. CNAMEs are aliases. A CNAME points a name at another name. You've asked for www.example.com. A CNAME will say, well, go and look here instead. Google.com is responsible for this one. Someone else is responsible for this one. CNAME is just a canonical name. I know these data exist, but please go and ask for it again under another name. MX record is a mail exchanger that's used for determining where to send email. Serve records are a generic way of giving information about different kinds of services that might exist on the internet. If you run a Windows network, you'll know serve records from Kerberos because it likes to use serve records to keep track of where your Kerberos servers live. If you're unfortunate enough to run LDAP, you will know serve records from there as well. The important records I do want to talk about, though, are the NS records, the first one on here, and the start of authority record, the last one on here. The NS records is the label that chains the tree together. The NS record is the branches of the tree diagram we saw at the beginning of the talk. The NS record says this server is responsible for that level of the tree. And the start of authority records is the beginning of a zone. It has parameters about and timing information about a certain level at the tree. I'll go into that in a bit more detail later. But these two records, the NS records and the start of authority records, are what builds your DNS tree. They're the branches of your tree. The other records on this slide are the leaves that hang off the branches. The actual data in the tree are A records, quad A records, CNAMEs, MX, all, and dozens of others. Well, not dozens because there's only 16 bits of them, but many others exist. But the only two that matter for today are the top one and the bottom one. So the start of authority records is at the beginning of a zone or at a delegation level, and it defines a couple of parameters about that zone or about the data that exists at this level of the tree. Like every other resource record in the DNS, it has a name, it has a time to live, it has a type, and then it's got some data that go with it. In the case, so that the first datum that goes with the start of authority record is the name of the master server, the name of the authority server of this zone. So this specific records I'm showing here says that the example.com zone, everything that lives underneath example.com, is authoritatively managed by this server. The final source of truth for everything underneath example.com is managed by ns1.example.com. That, you know, if you don't believe your cache, if you don't believe your recursor, your final recourse is ns1.example.com. That's where the data lives. The second field here is a responsible person's email, and that's just a little historical joke of the internet. What it is in practice in 2023 is a random string of letters and numbers separated by dots. Historically, that's where you would put the email address of the person to cry to if anything in the zone was wrong. So by convention, you take the email address, replace the first dot with an @ and then whatever else goes behind the email address. That works really well as long as people don't have dots in their email addresses. And that works really well as long as people stay at the same organization forever, or if people are smart enough to use role addresses. And it only works really well on an internet where everyone is nice and spam doesn't exist and people don't go and cry at random operators. So this record, you know, it has to exist, but it doesn't need to be true. It's just there for historical curiosity. Much more interestingly is the rest of the data in the start of authority records. There's a serial number that says how recently has this data been updated. It's a 32-bit number, and by convention, because dates fit really nicely in a 32-bit number, it's a date stamp of when the data was last touched. So in this case, You see the age of the slides. I will copy this particular example from 2009-0102. So the 2nd of January 2009 is the last time this fictitious example zone was touched. And the last two characters here are just an increment, so you can change the data 99 times in a day. Yes, question? It can be anything else. Yes. So the question is, by convention, it's a date, but it can be anything else. The answer is yes, as long as it increases as long as it increases. It can never ever decrease. It can only ever increase. So there's two popular ways of doing it. Most people use human readable date stamps, 2009 0102, and then you've got 99 tries to get it right on every single day, right? And then, and if you're still there after the 99 try, you could just pretend it's tomorrow and keep rolling over. Another convention is to stick a Unix timestamp in there, the number of seconds since 1970, and just increment it with the current time. A not very smart way of doing it is to put 1, 2, 3, 4, 5, 6, 7, because eventually you'll forget or you'll count backwards, and it's not fun. You can, if you need to travel backwards in time in your serial numbers, you can do it, but it's tedious because you'll need to do the 32 bits rollover complement sum. You can do it, it's just tedious. I always recommend people use dates because they tell you without much thinking how long ago the data were modified. If I see a Unix timestamp, I don't know what the Unix time, if it's less than 1 billion, I'll know it's really old. But beyond that, I can't draw any conclusions. With a timestamp like this, 2009, I know, well, this data haven't been touched in 10 years. Whereas if it's yesterday, I know that I might need to go and talk to someone. After the serial number, you've got a refresh timer. This is used by authoritative servers to keep them in sync. So an organization might have an authoritative master server, one server that is actually got the zone file on it, which is modified by humans, and then some slave servers or secondary servers that pull the data from that primary or master server and keep it in sync. This timer, the 7200, is how often these secondary servers go and ask the master server, hey, do you have something new for me? Hey, do you have something new for me? And the way that works is the secondary server tells the primary server, here is the timestamp I have, or here is the serial number I have, is yours newer? And the master server will say, well, here's my serial number, you draw your conclusions, because it'll just, it'll do a query for this SOA records and get back the data from the master and say, okay, my data is new enough, I don't need to download the whole zone, or the data on the master is newer, I need to go and download the new zone. So that number, the refresh timer, is up to you, right? It's how often do you want your DNS servers to talk to each other. The second timer is the retry timer. If your secondary server cannot talk to your primary server, how long does it wait to try again? In this case, it's 30 minutes. So if, every 2 hours, we go and check if there's something new on the master server. If we fail, we go and wait half an hour to try again. And we keep trying and we keep trying and keep trying until we get to the third number, which is the expire timer. So the expire says, if after 1 week, we have not heard anything from our master server, assume that it is on fire, or assume that it has gone away, it no longer exists, cry for help, stage an intervention. At that point, you need a human to step in and fix things. After 1 week, the slave server, or the secondary server, which is a much nicer word, secondary server will decide, yeah, I'm not going to pretend to be an authority anymore. My authority has gone away. The only really interesting number on this slide, though, is this last one, is the 300. And that's what we call the minimum time to live, or the negative time to live. So until now, in the finest tradition of teaching, I have been lying to you, and I've been saying, you can remember data for up to this long. You can, you hear some data, you can now remember this. Here's some data, you can remember this, you can remember this. But what if you get no answer? how long do you remember no answer for? The negative time to live on the start of authority is exactly that. It tells you how long you should remember that the answer is there is no answer. So if you go and look up www.example.com, you will get an answer. You'll get an A records, and you can remember it for an hour. If you go and ask for, I don't know, uuu.example.com, you will get the answer, hey, that doesn't exist. But how long can you remember that it doesn't exist? You know, are you going to ask every single time and get the same answer? No, the resolver is going to remember for, in this case, 300 seconds. For 5 minutes, it's going to remember, this does not exist. Stop asking. This does not exist. Stop asking. This does not exist. Stop asking. So the negative time to live number for an operator, this is the interval between things coming into existence in your network. So this is the, I don't know a better way of putting this. This is the birth rate of your network. This is how often you put things in place that were not there previously. But it's the number is also by type. So if you add IPv6 to a name that already has IPv4, the negative time also counts. So you set this to a sensitive value. I usually say an hour is a sensible time. This example is 5 minutes. It doesn't really matter what this number is. You just have to remember that this amount of time is how long you have to wait for a negative cache to expire. So if you're doing some pre-deployment testing and you're asking for the name of a server in the DNS that isn't there yet, you will have to wait up to this amount of time for the DNS to tell you what that server is if it appears later. I realize that this is very difficult to grasp. It's difficult to explain. It's the time you have to wait for a negative answer to expire. I don't see anyone crying, but I do see confused looks. Is it clear? I'm just going to skip over this, and you can ask me later if it still confuses you. Let's move on to the NS record. The NS record is mercifully simpler than the SOA record. The SOA record packs a whole bunch of things into a record, and I talk about it for 15 minutes. The NS record is much, much simpler than the SOA record. The NS record just has a name. It says, go look there. It has the name of the DNS server that controls the next level down the tree. And that's all it contains. And for operators, it's important here to realize that it has a name in there. It doesn't have an address in there. So there's a level of indirection. Your name servers also have addresses. If we go back to my pretty little picture here, we are going to ask the root server for the name servers of the root servers. We're not going to ask for the IP addresses. We're going to ask for their names, and then we're going to go back, and for those names, we're going to ask the IP addresses. So there's, it's indirection, it's recursion all the way down. The NS records gives you names of name servers. It doesn't give you addresses. The reason for this is that the names might have different types of addresses. It might have an IPv4 address, it might have an IPv6 address, or it might have multiple of each. So that's the NS records, and that's the only other one I'm going to talk about, because all the others are, just tedious repetition, and me reading out slides is not good for anyone. A records address, quad A record, also an address 4 times longer. C name records, an alias points one part of a tree up to another part of a tree. CNAME special rules, I'm not going to go into it today because I can talk to this slide for 3 hours. A pointer record, though, I do want to pause at quickly. Yes, please. The pointer records is the reverse mapping. So an A record, an address, this host has this address. I said at the very beginning of this presentation that the DNS can also tell you what the host name is that belongs to an address. And that's what a pointer record does. It does the inverse lookup of the A records. And the way it does this is a bit of a hack. What you see here is example.com has an address. It's 192.0.217. That's the address. To construct the reverse mapping of this address, we do exactly what it says on the box. We reverse the address. So we take our 192.0.217 and we flip it over, and we get 17.2.0 and 192. And then, because everything in the DNS needs to have a name, a proper name, and needs to live somewhere, the root servers are not going to be responsible for all of the reverse mappings. That would be silly. We slip inadder .arpa after it. And the reverse zones work exactly the same way as forward zones. There's no magic here. There's nothing special. They walk the tree the same way. So when you go and look up the reverse of a mapping, you walk the same tree. You go and ask the root zone, hey, where does ARPA live? You go and ask the ARPA zone, hey, where does inadder ARPA live? You go and ask 192 where that lives. You're gonna and you just walk from right to left. You walk the way down the tree to get your reverse mapping. So that's why in the APNIC database, when you get your address space, when you get your prefix, you can assign DNS servers to your prefix. What APNIC does is APNIC has 192.0, fictitious example. This is a documentation prefix. When they delegate your address space, at the same time, APNIC is going to add NS records in the 0.192.inadder ARPA zone, saying that the people responsible for 2, their name server is here. So in your My APNIC portal, you add your NS records. You add your name servers. What that does is APNIC goes and adds to the DNS your NS records. There's no fiendish magic there. It's just DNS. It's DNS all the way down. It's the same query forwards and backwards. So when you look up pointer records, all you're doing is flipping your address backwards and walking the same DNS tree to get your answers. And the data that goes with the pointer record is just a name. You will have noticed that you are in control of this name, right? So you can put anything you like there. It's just a name, it's a string. You can lie, anyone can lie. The only thing the DNS is the DNS is for answering questions. The DNS does not judge. So the DNS is only as truthful as the operators who put data into the DNS. And as we'll see later on in the second part of this tutorial, DNSSEC only authenticates what the operators say as true. So when you add DNSSEC to the DNS, you will be able to authoritatively state that an answer is what the operator put in the DNS. The operator can still lie. The operator can still give you complete nonsense answers, but they can also authoritatively give you nonsense answers, and they can sign them. You can cryptographically verify any nonsense. So it's always important to remember as you go through the DNS and DNSSEC that yes, it's an authoritative source of truth, and yes, it's a source of information, but the information in the DNS is only as good as the operators who put it there, and is only as trustworthy as the operators who put it there. And that still holds true with DNSSEC as well. Operators can lie, but they can now also authenticate their lies, and you can go and verify their lies. And I'll keep reinforcing that throughout the tutorial. But pointer records is an A record flipped backwards and resolved in the same way as any other records. IPv6, the gift that keeps giving. Unsurprisingly, IPv6 works exactly the same way as IPv4, except the numbers are 4 times larger and 4 times more difficult to remember, because the inadder ARPA tree was already taken for IPv4, and the first or the last 32 bits of IPv4 and IPv6 are overlap. We stick the pointer records for IPv6 in the IP6.ARPA zone. Everything else about the record is exactly the same as IPv4, except the numbers are larger. So we take the IPv6 address as, you know, in the format we are most familiar with, but with all the zeros expanded. So in this case, we have 2001 DB8 mumble, 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 mumble. We fill in all the zeros. So all the imaginary zeros here and here and here, we fill in all the imaginary zeros to make it an even more difficult to remember address. We take away the colons, we flip it backwards, and we construct exactly the same kind of records as we had for IPv4. I hope that's clear to everyone. And again, just like with the IPv4 pointer records, the authority is delegated in exactly the same way as with named records. Your prefix will be, you know, somewhere down here is where your authority starts. When you add your NS records in my APNIC, your NS records make you responsible for the left sides of this record. And inside your organization, you can make it as complicated or as simple as you want by sticking NS records at every level of the tree, or if you've got any sense, maybe at every 8 bits or so, or every 8 bytes or so. But it is up to you. It is a tree, just like the forward DNS. MX records, I'm not going to dwell on. Serve record, again, not going to dwell on it. There's lots of it. Go read the slides. A text record is quite fun. So text records are arbitrary string form data. You can put anything you like in the DNS. Some people like to put poetry in the DNS, but currently text records are used for things like SPF to authenticate mail flows, or sometimes text records are used to document ownership of things, or as a challenge response kind of system. If you sign up for, I don't know, for Google Postmaster tools, they will ask you to stick a text records in your DNS to verify that you actually have this domain. If you're doing Let's Encrypt for issuing certificates using DNS, as I taught on Tuesday, text records are the challenge response system for authenticating your certificates. You can put anything you like in a text record, but you know, it's a record like any other. Wildcard records, I am really not going to talk about much during this talk because they're even more evil than CNAMEs. A wildcard is exactly what it says on the tin. Everything under here looks like this. It's star.example.com, anything foo.example.com, bar.example.com, anything.example.com will have the same data associated with it. It's practical, or it looks practical, but it quickly becomes difficult to manage. And wildcards are really painful once you start adding DNSSEC. So if you find yourself in a situation where you think, hey, a wildcard record would really be appropriate here, take a step back and think back about all your decisions in life that led up to this point, and reconsider your needs. I have rarely seen a wildcard record being the best solution to any problem. It usually leads to more problems than solutions. So wildcards exist, just treat them with some care. And at that point, I will pause again briefly to catch my breath and to let Anurag heckle me.
Anurag Bhatia, Hurricane Electric. What makes you hate wildcard? There's a good use case, which is I personally use them because if I have a dozen of apps hosted at a single location, I would have a star.airportcode.my-domain, and I would have a wildcard SSL for that specific location for that. There is a security advantage in doing that, which is if I have 40 apps running on that location and I issue SSL certificate for each of them, I'm announcing to the world in certificate transparency that these 40 apps exist. While if I do a wildcard SSL with wildcard DNS, it's just one. People don't know if it's 40 applications using the same certificate or just one. Or I just expose myself in the public stream probably.
I agree with your conclusion, but not with your premises. So the conclusion you reached is the correct conclusion for the steps that led up to it, but each individual step is wrong. So if you have 40 different apps under a wildcard, you can never move each individual app without affecting every other app. So you impede, you are setting future you up for a rough time, because you'll need to eventually, once one of your apps grows up and needs a different configuration, you'll need to untangle that wildcard at some point in the future when it's had time to propagate in your network. So once you stick something in a wildcard, the wildcard covers everything. It doesn't just cover what's there today, it also covers what will be there in the future. So you deprive yourself of the opportunity to have something else in the same namespace.
Okay, let me trace the steps back. You said, let's say one of the application outgrows. So out of those 40 applications, one needs more resources. I don't have that on that server anymore. I'll just create a new A record. Now that specific app now has a record pointing to a new server. I don't need to touch any of remaining 39 apps or the wildcard. So wildcard still works.
Yes, but if the wildcard covers that name, it shadows that name. You can't pull it out of the wild.
You can have more specifics. You can have star.something.com. All 40 apps use that. And now I got my specific app .something.com with an A record. So you can just untangle one app out of a bundle of wildcards. Thanks.
Sure. I still maintain that future you will cry. It might go well for you, but future you is likely to cry. And I would encourage you to look at the DNSSEC implication of a wildcard, because it gets really twisted and horrible. Yes, you can reason up to logical, a wildcard might be a good thing to do, but still, if you reach that conclusion, I would still encourage careful reflection and just, is this really what I want to do? And also think about the longer term consequences. Remember, the wildcard covers what's there now, but it also covers what's not there yet. So the wildcard will interact with your negative time to live. The wildcard will, you need to think about not just the wildcard itself, but how it interacts with the rest of your system. As for the SSL certificate arguments, we talked about that briefly on Tuesday in my other tutorial. I don't think wildcard certificates are a sensible idea, because every single host will have the private key of every single other host, because that's what a wildcard is. So very soon your private key will be a public key, and that sort of defies the purpose. So with wildcards, both in SSL and in DNS, yes, they exist. And I'm sure that if you think long and hard enough, you can think of a legitimate use case for them, but still think twice before deploying a wildcard, because future you might have an interesting adventure detangling a wildcard. But very good question. Oh no, there's a follow-up question.
I won't take much time, and I understand this is on DNS and DNSSEC actually, not on wildcard. But on your point about the private key part, keep in mind, majority of production cases would have SSL terminating for number of application on a single logical system. This could be a physical server. This could be a Docker container running Nginx or KDE or the sort of thing. Now you are going to deal with whether you have dozens of certificate pairs sitting at exact same location under exact same system, under exact same credentials, versus you just have one. And if you start doing that with location tagging, now you're not sharing that anymore. So I would not suggest anyone to have, say, star.theirdomain.com, but they could have something like, say, star.whatever, the nearest airport code or any other logical system, star.server1.domain.com. And instead of having 10 apps, to have 10 SSL within there. So one needs to probably go more in the threat model, but it won't be that risky for the reason that it is the same logical system. You're not spreading them out. And I would never suggest anyone to go and cat your private key and copy paste it. Just issue a new certificate.
Good. You've done the reflection I was advocating for, actually. So the point where you said that I wouldn't put a star.mydomain.com is exactly the conclusion I wanted you to reach. You know, star.something.something, that's fine. Star.something.something.something is even finer. Just if you're going to use a wildcard, try to restrict what that wildcard covers as far as possible. I don't deny that there are use cases for wildcards. There's certainly use cases for wildcards, but the drawbacks are there as well. So if a wildcard is the best conclusion, try to make that wildcard as harmless as possible. Very good questions. Thank you. I have another, do I have 10 minutes or 50 minutes? I don't even know how much time I have. 10, 50, 10. All right. I will move on to zone files briefly because this is an operator conference and just to show you what these things look like. In the vast majority of DNS implementations, this is how you plug your data into the DNS, right? So you will have a file that has labels on the left and data to the right of it. So in this contrived example, we have example.com. It's got a time to live, start of authority, ns1.example.com. Remember, that's this is the final source of truth for this zone. Admin.example.com is a random string of letters and numbers that may or may not be the responsible person of this zone. Serial number is how recently have these data been modified? How recently has this zone been touched by a human being? Refresh timer and retry timer and expiry timer. These are internal to your organization. These are between your name servers, your primary and your secondary name servers. How often do you keep your servers in sync? There's an update mechanism that bypasses all these timers, but in the simplest possible implementation of the DNS, these three timers determine how often your DNS servers, the servers that are authoritative for this zone, how often they stay in sync. The minimum time to live, or the negative caching time, is how long should a resolver remember that an answer does not exist. What is the birth rate of your network? What is it's a measure of volatility in your network. How long should non-existence be remembered? For plain DNS, this number is essentially arbitrary. It gets a lot more interesting with DNSSEC, which we'll explain after I've had some more coffee in me. Couple more records in this specific zone. Example.com has 2 name servers. So the RR set here, yes, question? The question is, why are there parentheses around here? Good question. That's the presentation format in the zone file. So on the wire, so if you go and look at a packet capture of the DNS, the fields in here, this is a single field and these data are encoded in a funny way. It's a way to turn the textual representation into bits that end up in the packets. But yes, good question. I didn't dwell on it at the beginning of this talk. I just skimmed over it. Every single type of records has a specific canonical representation format, and the start of authority record, the presentation format, has these parentheses. For text records, parentheses are also used if you have a very long one. So if you have a text record that doesn't fit in a UDP packet anymore, you need to use the parentheses to let it fit. Very good question. Presentation format, just a implementation detail. This particular zone has 2 name servers, ns1.example.com and ns2.example.com. It has 2 of them, which means if you ask for the NS records for this name, nsexample.com, you will always get 2 answers. There exists no way in the DNS to only get one of the name servers. You will always get both of them. If you ask for NS records, you will get both NS records. The recursor can decide to return these to you in any order. It just needs to return both of them to you. MX records, again, there are two of them. If you ask for MX records for this zone, you will always get both of these. They might appear in any order, but you'll get both of these every single time you ask. Text records, there's only one of them, and 3 A records. So if you ask for the A records, you'll get 3 A records. Cunningly, Awal has put a configuration error in this example, or maybe he's copied and pasted the error from a previous version of these slides. Or am I blind? Oh, yes. Oh no, I'm not blind. Sorry, there's no configuration error. I'm just blind. I was going to say that the ns1.example.com has 2 different times to live, but they're 2 records. So forget I said anything. I didn't do it. Nothing happens. The time to live here of your ns1 is 2 hours and ns2 is only 1 hour. If you have 2 records with the same name, they must also have the same time to live because the DNS always returns them both at the same time. If you have 2 different time to live for 2 A records, yes. Yeah. Anurag has a question about the TTL.
So let's say this is a real zone and you got this, TTL of 72 and 36. It's interesting. Example.com is using example.com as a name. So this won't work unless you have the glue records.
Yeah.
So 2 questions. One, if glue records have a different TTL compared to the TTL in your NS records, which one actually applies? Let's say here we can see it's 72, 36. Let's say in the glue records, it's a 60. Which TTL would actually be used in the resolution? And second, what's actually default TTL in glue? Because registrars don't give you option to mention TTL in the glue. They just allow you to register a name server. Do you know that?
Yeah, the answer to both of your questions is it depends. It's an implementation detail in both cases. And I've not looked recently. Bert does a very nice presentation about the DNS camel at IETF about all the different implementation details and all the weird and wonderful edge cases of the DNS. So whatever I say, if it differs from what Bert says in that presentation, he is right and I am wrong. So it's an implementation detail, and it will depend on the caching behavior in between. So if you ask the implementation I'm most familiar with is Unbound. If you ask Unbound and you have a leaf zone example.com with TTL 3600 in the NS records, and you've got a parent zone which has NS records pointing down with a longer TTL, Unbound will serve the leaf TTL by default, unless you specify unless you disable the recursive bits in the query, in which case it will give you the parent. The TTL is always on a record, right? So the example.com zone, so this zone has records ns.example.com. So that's the leaf zone. These are the child records. The parent records are the glue records. The leaf is this one, or the child is this one. The parent is the glue. If you run your query with the QR bits off, so you ask for no recursion, or the RD bit rather, you disable the recursion desired bits, Unbound will give you the parent zone or the glue records TTL. If you have the recursion desired bit set, Unbound will give you the child zones TTL, which makes sense. And as far as I remember, but again, Bert's IETF presentation is more correct than me. If I remember correctly, Bind will give you the last one it saw, whichever one is most recently in its cache. So if Bind saw the glue after it saw the child, Bind will give you the TTL of the glue. If Bind saw the child more recently than the glue, Bind will give you the child. But the answer to the follow-up question you didn't ask is don't do that. It's confusing. But your second question was interesting as well, though. It's what is the default time to live of a glue records? And the answer to that is also, it depends, but by seemingly rough consensus, every TLD I've seen seems to have picked on a day or so. But in practice, when you update your if you update your glue records, they might change. So the parent will refresh almost immediately, but the time to live will be whatever they set it as. So you will still, if you do this and you have glue records, you will need to wait a whole day before you can change your name servers. Yeah, it depends.
Can I quickly kill 1 minute of your
Yes.
session? Is glue record is not authoritative data. So if I ask for a name server information, that should be served from the child zone, not from the parent zone. So that's why your answer is probably right, that it's going to give the last record or more specific record, if I'm not wrong.
Right. So but if it's a glue record, it is going to be authoritative.
You just NS records for the actual zone. NS existed at the leaf.
Yes. Right.
NS and SOA do not exist at the upper zone. In this case, it would be COM. So .com GTLD do not have NSO or the SOA. So you cannot ask GTLD servers to resolve this, but you can ask GTLD servers just to resolve the glue, and it will give you reply in additional section and not in the authority section by design.
The glue record is authoritative if you query the parent zone. So if you query the COM zone for the records, because the record is inside. So if you disable recursion and you ask the parent zone, the glue record is authoritative. If you recursively resolve, then it is not authoritative.
I might be wrong, but why I'm saying is because if you sign a zone, glue record is not signed, right? Because it's not authoritative. That's the reason, right?
Pavel is right.
Yeah.
Someone asked me this question, and I remember last year I wrote a long blog post about it on my personal blog. And that time I did. So assuming this case is still true, I don't want to bring up new domains in the discussion. Assuming you have example.com using example.com's on name server. Now, if you go to root zone, that is in this case, .com would be GTLDs, .com GTLDs. If I go and query any of the .com GTLDs, you can try it in my domain. I have a .com and I use my own. I have glue in there. Oh, you can try with our domains, sure.
So ns1.he.net is very short and easy to type while I'm holding a microphone. So if
it's any, you have a type.
oh, did I see? I keep doing that. Someone needs to typo squat. Yeah.
It's still.
Did I do something dumb? Oh, NEHE. There we go. It helps if you type
Yes,
the right thing.
it's resolved, but you cannot expect same answer if you query GTLD of .NET directly. You will see that in additional section. You will not see that in answer section because it does not has the authority to reply back. So do dig NS, yeah, and not query any of these. So now the answer will come in the additional section, but not in the answer section.
These data are still okay. Okay, yes. So the glue record is still
and it's a non-auth
additional.
reply if you see the DNS flag. So because this upper zone is not authoritative to it, but it has the records.
Yes, yeah. So this is one of those fun edge cases where if you're querying for glue, the AA bit will go away.
Yeah.
And yes, yeah. So yeah, if these sorts of horrible spiky edge cases excite you in some way, I strongly recommend going to YouTube and watching Bert's wonderful presentation on DNS nastiness. It's full of edge cases. And the good news I have for you is that DNSSEC adds more of these nasties to it. And that's what we'll take after we get some tea or coffee and sugar into our bodies. The next half of this is going to be DNSSEC. The first half was just DNS. I hope this was useful, and I maybe see most of you after the break.
Pause.
Why do I do this?
I promise you. I hope the.
Thank you very much. It's very helpful. DNS is scam.
For your, hearing loss on your. It was interesting to hear it. Again, it's a data center one. Yeah. You get that data. Yes, yes. Until we got in there, I did not. University. University. Interesting. Yeah.